Hello and welcome back to Force Vectors, my fearless physics students. So here we have physics, and we're going to do another component vector problem. And we're going to think of a scenario. Let's see, component vector, let's see, problem. Okay, we're going to think of a scenario, and I'll try to do this one a little bit faster than the other one, so this might not be quite as in-depth, but let's say we got a couple of guys, and let's say their names are, let's see, say we've got one named Enoch, right, and that's Enoch right there, and then we've got one named, let's see, what's this one's name? Jacob, okay, and Enoch and Jacob, they decide to build a sweet tree house. Okay, so this is the branch of their sweet tree house, and these are and then this is their sweet tree house that they built right here, right? And, you know, the roof is a little crooked. It's it's their first time building a tree house, and they built a window, but they forgot to build a door. Oops. But anyways, they built this sweet tree house, and so this is a branch right here, and so let's say that this is the trunk of the tree, right? And here's the ground down here, and so we've got the foliage right here. So here they are, and they're up in this sweet tree house, and they say, "I know now we need the final touch. What is going to be the final touch of this tree house?" And so they said, "I know, let's get some Doritos." So they go to the store and they buy some Doritos, but they buy the biggest box of Doritos they can buy. And so the box weighs 3.2 kilograms, right? And they try to lift it up this little ladder that they made that goes up the tree trunk, but it's too heavy. And so what they decide to do is they decide to connect ropes. So Jacob's got a rope connected to this, and Enoch's got a rope connected to this. And they decide that if they just heave up on this rope, they should be able to pull their box of Doritos up. And so they calculate this out, and they figure that that they can do this. And so Jacob pulls, and Enoch pulls with all of his might. And so what they end up doing is Jacob ends up pulling, right? He ends up pulling with a force of 17.7 newtons. And Enoch ends up pulling with a force of 20.4 newtons, because Jacob was like, "I'll make it look like I'm pulling hard, but then I'll have him pull harder." And so anyway, so Enoch is pulling up on this, and Jacob is pulling up on this. And let's say that that the angle that Jacob is pulling up with the ground is off the ground is 55 degrees, and Enoch is at 60 degrees from the ground. Okay, and so the question is, let's see, what is the question? The question is, what is the total amount of force that these guys are able to pull on this box, or what is the total amount of force needed for these guys to pull this box up? And so what we're going to have to do is we're going to have a force which lifts the box up and gives the box an ability to go up against the force of gravity. So we understand that the force we're going to have to pull this up is going to have to cancel out the force of gravity. Okay, so let's go ahead and redraw all of our force vectors over here just real quick. So we've got the box, and we've got this vector right here, and we know that this one is 55 degrees, and we've got this vector. Oops. Let's see. And we've got this vector right here, and we know that this one is 60 degrees, right? So there's that angle right there. And so both of these forces, and let's go ahead and break these up into their component vectors, both of these forces are going to have force in the x direction and the y direction. So, so they're going to have forces going up, and they're going to have forces going to the side. And what we need to do is we need to make sure that we have a combined force. And so the question is, that with Jacob pulling at 17.7 and Enoch pulling at 20.4, do they have a combined force that is necessary to lift this box or not? And so, so what are they going to have to compete against? Well, they're going to have to compete against gravity. And so gravity is going to be pulling down on the box. The force of gravity is going to be pulling on down the box. Let's figure out what that component vector is right off the bat. So that component vector is going to equal 3.2 times 9.8, right? So, so what is that? Well, if you calculate that out, we know that this is going in the negative direction because the positive direction is up. They're going against gravity. So the force of gravity, if you calculate that out, is going to equal negative 31.4 newtons. All right, so that's negative 31.4 newtons pulling down. So they're going to have to be able to exceed that in the y direction. And they're going to have to be able to, another thing we're going to have to be able to figure out is, are they able to pull it straight up? Because if their x components are not equal, right? Because if you look at this x component is pulling in this direction, right here, and this x component is pulling in this direction, right here. And so if their x components are not equal, this box is going to be going at an angle one way or another, right? It won't be going straight up. So that's another question we're going to have to ask as we analyze this problem. All right, so first of all, let's check out the x components and just see if we are going to be going straight up or if we're going to be pulling it to the side at all. So how do I figure that out? Well, I know that this vector right here is 17.7, and I know that this vector right here is 20.4. So how do I figure out this right here? Well, I could use my trig functions. I know that this is 55 degrees, so this Rx in this direction is going to be, and we'll call this the positive direction right here. So let's say the east is a positive direction. And so we have the, let's go ahead and use the cos. So I have the cosine of 55 is going to, let's see, the cosine of 55 equals, let's see, ca equals adjacent over hypotenuse. So equals, let's call this x direction A over 17.7. So that means I'll be multiplying cosine of 55 times 17.7. So this x direction here is 10.2 newtons in this first x direction. So now let's look at this other x direction. So this other x direction right here, it's going to be the same kind of thing. So we're going to take the cosine of 60 and multiply that times, so we'll just go ahead and do this. And so this is the negative Rx direction because this is pulling the other direction. So we have the cosine of 60 times 20.4, right? And so then what does that give us? Let's see. Let me figure that out one more time, just looking at my calculations. And I think I didn't calculate that right the first time. 20.4 equals 10.2. Well, how about that? So I got negative 10.2. So what we just proved is that the two of them, even though they're pulling at different forces, since he's pulling at an angle of 55 and he's pulling at an angle of 60, in order to get the same horizontal force, Enoch has to pull harder than Jacob. So, and it could be because this branch is a little bit lower, he's pulling on it more at a slanted angle or whatever. But we find that that if this is 10.2 and this is 10.2, these x directions cancel each other out. So we know now that the box is going to be going straight up. So now the question is, what are our vertical directions, right? Our y directions. So if we look at the y directions here, let's go ahead and go down here. So let's say our r in the y direction components. What is that going to equal? Well, I have 17.7, and I could take the sine of the angle theta equals the opposite over hypotenuse. So I'd end up multiplying the sine of 55 times 17.7, and that's going to equal 14.5 newtons. Plus, on this other side, we're going to have the sine of 60 is times 20.4. The sine of 60 times 20.4, because I'm using my SOH trig function. SOH, so opposite over hypotenuse, because the opposite, here's my angle theta right here, and here's the opposite of that. And that's what I want to know. And notice these are both going in the same direction, so they add to each other as opposed to our x's that subtract from each other, right? And so I take a look at this, and I have, what is that going to be? 20.4 times, let's see, times the sine of 60. Say, yeah, sine of 60 times 20.4. So let me do that real quick. Sine of 60 times 20.4. We get 17.7. .7 newtons. Okay. And so I'm going to add those up, and that's going to give me, see, 17.7 plus 14.5 is going to give me a total of 32.2 newtons up. So these guys right here, and hopefully you saw what I did. In the y direction, I had two vectors. I had this vector from Jacob and this vector from Enoch. And so we just figured out those two y direction vectors and added them together. Gives us a total of 32.2 newtons. So we have 32.2 newtons in the y direction. And now I know that the force of gravity is going to be subtracting from me 31.4 newtons. So let's go ahead and figure that out. So I have 32.2 minus 31.4. And so I get a net force. So I have a force net of 0.77 newtons in the up direction. And remember, our two side directions cancel each other out. And force equals mass times acceleration. So this is going to equal our mass, which is 3.2, times an acceleration. So if we divide 0.77 by 3.2, we get an acceleration of 0.24 meters per second squared up. And so you could actually use that to find out, if you knew the distance right here, you could figure out how long it would take them to pull it up if they kept that at a constant acceleration. But anyways, all you know is that right off the ground they have an acceleration of 0.24 meters per second straight, and per second squared, and they have enough to counteract the force of gravity, so they can lift their Doritos up, and they are rocking and rolling here, so they have a total of 0.77 newtons in the upward direction left over, because they ended up with 32.2, and yeah. So looks like we've got that problem easily figured out. But anytime you have multiple angled whatever, you can always take those angled vectors and you can break them up into their vertical and horizontal components. For a situation like this, we might have ended up with it going at an angle, and so then we would have had to figure out what that angle was using the inverse tangent of the x over the y. But we could have figured that out as well and figured out if it wasn't going straight up. But in this case, it did happen to go straight up. So hopefully that helps.